Dear friends, welcome to the PowerPoint presentation on Physics for Class 12. In this section, we will study about capacitor and capacitance, which is covered under Chapter 2 of Electrostatic Potential and Capacitors. The topics covered in this session are capacitor and capacitance, combinations of capacitors, energy stored in a capacitor, effect of dielectric on capacitance, capacitors in dielectric, and finally we will end the session with discussions on Van de Graaff generator. Please note down all the important points discussed, as the same will help you in writing your examinations. Thank you. Capacitor and capacitance. A capacitor is a device which stores potential energy in an electric field. A capacitor consists of two conductors separated by an insulator. The conductors have charges plus Q and minus Q with potential difference V is equal to V1 minus V2. Please see the figure on the right hand side. There are two plates. On the left side, plate A of area A is charged with positive charges, that is plus Q or plus sigma. On the right hand side, you have another plate which is yellow colored, and its charge density is also sigma. The distance between the two plates is D, as shown. This is the distance D, and the area of plate is A. These are the area. This is the area, length into breadth. So I repeat, there are two plates, blue colored plate and yellow colored plate, separated by a distance D. The charges or charge density is sigma and electric field is E. Electric field is pointing from left side to right side, and these arrows are shown are electric field. The charge Q is proportional to the potential difference V applied between the parallel plates. Charge Q is proportional to the potential difference V, or Q is equal to CV, where C is the proportionality constant called capacitance. Therefore, C is equal to Q by V farads. The surface charge densities on plate 1 is plus sigma on the plate 1. This is the plate 1, and its charge density is plus sigma, and the charge and on surface charge density on plate 2 is minus sigma. See, this is shown by the sign. Here there is a positive sign that shows it is a positive plus sigma, and here it is minus sigma. E electric potential on the outer region of plate 1 and plate 2 is 0. That is, E is equal to 0 outside the region. Let A be the area of each plate, and D be the distance between them. In the inner region, that is, this is inner region of plate 1 and 2, the electric fields due to two charged plates add up, giving E is equal to sigma over 2 epsilon naught plus 2 sigma over 2 epsilon naught, that is equal to sigma over epsilon naught, that is equal to capital Q, that is the total charge, divided by epsilon naught A. This is the electric field intensity. Hence, I will repeat once again. The electric field intensity is given by sigma divided by 2 epsilon naught plus sigma divided by 2 epsilon naught, that is equal to sigma over epsilon naught. But sigma is equal to Q over A, that is total charge Q on the plate divided by the area of the plate. So E is equal to Q over epsilon naught A. Let this be equation 2.26A. From here we will calculate the potential or the potential difference. V is the potential difference. V is equal to E into D. From our knowledge of previous sections, we know V is equal to E into D. Therefore, E, substituting the values of E, we get V is equal to Q divided by epsilon naught A. We are repeating here and we are multiplying by this D. So, therefore, the value of potential equals Q over epsilon naught A into D. Let this be equation 2.26B. So, we have also told in the para 2 that Q is proportional to V or Q is equal to CV. Therefore, C is equal to Q divided by V farads. Same thing we are substituting here. Therefore, C is equal to Q by V. Here Q is epsilon naught A by D. Substituting the values of V and Q. Suppose we transfer V here, Q divided by E, and this will be epsilon naught A by D. This is the equation number 2.26C. We have obtained this from the basic equation proportionality of charge with potential. Therefore, C is equal to Q by V, that is equal to epsilon naught A by D. Here you please see the value of capacitance C is dependent on epsilon naught, which is the permittivity, into A is the area and D. So, capacitance is entirely depending on the physical dimensions of the capacitor. The symbol of capacitor is given in this figure. There are two symbols. For fixed capacitor, we use parallel plates. As you know, capacitor is made of two parallel plates, and hence this is the symbol which we are using in electrical circuits. This is the fixed capacitors. There are also variable type of capacitors whose capacitance value can be varied. Here it is represented by two plates with a cross arrow. This is a variable capacitor. The capacitance C depends only on the geometrical configuration, that is shape, size and separation. Shape, we know we have parallel capacitors, cylindrical capacitors and all that, and size. Size is area and the distance and the separation of the system of two conductors, and also depends on the nature of the insulator, which is characterized by the dielectric constant or permittivity epsilon naught or epsilon r, as the case may be. The SI unit of capacitance is 1 farad. 1 farad is equal to 1 coulomb per volt, or 1 farad is equal to 1 coulomb per volt. In practice, we have seen farad is a large unit. Hence, multiples of farad like microfarad, that is 1 microfarad is equal to, it is written as 1 mu f, that is equal to 1 into 10 to the power of minus 6, and picofarad 1 pf is equal to 1 into t to the power of minus 12, are more commonly used in practice. Hence, let us repeat the contents of this slide. So, capacitor is a device which stores potential energy in electric field. It has two conductor plates, one positively charged and the other one is negatively charged. The equation for electric field intensity is given by E is equal to Q divided by epsilon naught A. The value of capacitance is given by C is equal to Q by V farads. The potential across a capacitor is given by V equals E into D, that is equal to Q epsilon naught A into D. And capacitance, the value of capacitance is also given by Q by V, R is equal to epsilon naught A by D. And the capacitance depends only on geometrical configuration, that is shape, size and separation of the system of two conductors, and it also depends on the nature of insulator, that is the dielectric separating the two conductors. The SI unit of capacitance is 1 farad, that is 1 coulomb per volt. Farad is a large unit. Generally, we use microfarad, that is 1 into 10 to the power of minus 6, and picofarad, 1 pf is equal to 1 into 10 to the power of minus 12. Now, let us study about combinations of capacitor. In combinations, we have two types. One is parallel and second one is serial. Let us first take up parallel combination of capacitors. Please see the figure on the right hand side. Here there are three capacitors, C1, C2 and C3. Three capacitors which are connected across a potential V, potential or a battery V. Here when we say parallel combination means the one end of all the three capacitors are combined, that is one side of the capacitor C1 here in this figure plus of the one side and plus side of the C2 and plus side of C3 are combined and connected to positive of the battery. And similarly, the minus sign, the plate with minus sign is combined on another side. All the three, one side of C1, other side of C2 and the other side of C3, all are combined and are connected into the negative side of the potential. So, this combination is called parallel combination of capacitors. Here the charge gets distributed. The charge on capacitor C1 will be Q1 and C2 will be Q2 and C3 will be Q3. Hence, this is the figure for parallel combination of capacitors. One important point for parallel combination which you have to remember is the potential is same across each capacitor. That means the potential is here V. V is same. If you see one end of the capacitor C1, it is potential is V. So, V is common for all the three capacitors. The charge is distributed in proportion to the capacitance. Hence, V is same but charge is distributed. Q1 across C1, Q2 across C2 and Q3 across C3 is the charge. So, charge is distributed in proportion to the capacitance. Therefore, total charge of the system will be Q is equal to Q1 plus Q2 plus Q3. It is given in this equation. Total charge is Q1 plus Q2 plus Q3. But we know that Q is equal to CV. As shown in the previous slide, Q1 is equal to C1V. and similarly Q2 will be is equal to C2V and Q3 will be equal to C3V. V is common for all three, hence it remains same, whereas the capacitance value and charge will be different. Therefore, substituting the values of Q1, Q2 and Q3 in this equation, that is Q is equal to Q1 plus Q2 plus Q3, we get C equivalent into V will be equal to C1 V1, C2 V2 and C3 V3. Therefore, taking V as a common and cancelling left hand side V and right hand side V, because it is a common factor, it gets cancelled and we get C equivalent is equal to C1 plus C2 plus C3. That can also be written as C equivalent is equal to sigma I into N, that is I equals 1 of Ci. Hence, for a parallel combination of capacitors, the effective capacitance is the sum of individual capacitance. Please note that the effective capacitance of parallel combination is larger than the largest of all the individual capacitance. Suppose amongst C1, C2 and C3, the value of C2 is largest, then the total value of CQ will be larger than the largest. Hence, to recollect, for parallel combination of capacitors, C equivalent is equal to C1 plus C2 plus C3. Let it be equation 2.27a. Please remember all this. This will be helpful in solving numerical problems. Having studied parallel combination, now we will study about series combination of capacitors. Please see the diagram shown. Here there are three capacitors C1, C2 and C3. All are connected together. Together means in the system shown in the figure. Here the plus plate of the capacitance, one capacitor is connected to plus side of the potential. Similarly, this negative side of the C1 will be connected to the positive side of the C2. Similarly, negative side of the C2 will be connected to plus sign of the C3, and similarly this negative sign of the third capacitor will be connected to the negative side of the battery. Here it is very simple way. One side is connected to positive and the other side is connected to the negative. So positive and negative are connected as shown in the figure. Here the potential V gets divided into different ratios V1, V2 and V3. So the potential gets distributed V1, V2 and V3 as shown. The value of capacitance will be C1, C2 and C3. Here charge is same in each of the capacitor. Q is same across C1, C2, C3 because charge or current is flowing from one side of the battery and it is entering. So same charge goes out and it comes here and then goes out and comes out. That same charge is not getting distributed. So here charge is same in each capacitors. Potential is distributed. Potential V is distributed in inverse proportion to the capacitance. As we know, C is equal to Q by V. So V is denominator, hence potential is distributed in inverse proportion to the capacitance. So as said earlier, V is equal to V1 plus V2 plus V3 and Q is same for C1, C2, C3. So V is equal to Q by C. Hence V1 will be is equal to Q by C1 and V2 will be is equal to Q by C2 and V3 will be is equal to Q by C3. Therefore, combining we get Q divided by C equivalent. Here V, its value is Q over C and we call it as C equivalent, that is combination Q over C equivalent divided by Q over C1 plus Q2 over C2 and Q3 over C3. Therefore, Q is common on the numerator on the left side and the right hand side. So, this Q of left hand side gets cancelled with the Q of the right hand side. Therefore, 1 over C equivalent will be equal to 1 over C1 plus 1 over C2 and 1 over C3. This can be written in the another form. 1 over CQ is equal to sigma I is equal to 1 to n 1 over Ci. So, here all are reciprocals. We can say in a series combination of capacitors, the reciprocal of equivalent capacitance is the sum of all the individual reciprocals. The reciprocal of equivalent capacitance is the sum of all the reciprocals of the individual capacitance. Please note one important point. The effective or equivalent capacitance in series combination is less than the least of all the individual capacitance. Suppose the least of capacitance is C1. So, the value of C equivalent will be less than 1 over C1. That is, the effective or equivalent capacitance in series combination is less than the least of all the individual capacitance. Hence, we will recollect for series combination of capacitors 1 over C equivalent will be equal to 1 over C2 plus 1 over C3. Energy stored in a capacitance. Having seen series and parallel combination of capacitors in the previous slides, now we will study energy stored in a capacitance. Please see here a capacitor is shown in the figure which is connected to the potential V. So, left side is a positive charge and right side we have negative charge density. The process of charging a capacitor is equivalent to transferring a charge from one plate to another plate of the capacitor. So, the charging means we are transferring positive charge from one plate to another plate or negative charge from right plate to the left plate. Hence, work has to be done against this potential difference between the two plates. This work is stored as electrostatic potential energy. So, we are transferring charge from one plate to another plate for which we have to do some work and that work is stored in the capacitor. If dq be the charge transferred against the potential difference V, then work done is equal to du is equal to dw, that is equal to V into dq, that is equal to q by c into dq. As we know, value of V, this V is equal to q by c and dq we are retaining as it is. Therefore, total work done W is given by U is equal to integral 0 to Q divided by 0 to Q into Q by C into dQ. I repeat, the total work done W is given by equation U is equal to integral 0 to Q of Q by C into dQ. So we can take C, which is a constant outside, and integral of 0 to Q into dQ will be Q squared by 2. Hence, the energy stored in a capacitor is given by the equation U is equal to 1 over C into Q square by 2. Equation 2.2a can also be written in another form. Here we retain U as equal to and substitute the value of Q is equal to CV. So Q square becomes C square V square, and denominator we have C. That C gets cancelled with 1C of the numerator. Hence, the value of energy stored in capacitor can also be written in another form. U is equal to CV square by 2. Let this be equation 2.28b. The equation of 2.28b can also be written as U is equal to QV by 2. Here 1C and 1V becomes Q because we know Q is equal to CV. So 1V will retain as it is and the denominator is 2. This equation is 2.28C. So energy stored in a capacitor is given by Q square by 2C or CV square by 2 or QV by 2. Any of these three forms can be used while solving numerical problems. Now let us study about energy density. Energy density is the energy stored per unit volume. That is, this energy stored, if we divide by a volume of the capacitor, we will get energy density. We know electric potential energy of a charged capacitor is given by CV square by 2. That is, we are using this equation here. U is equal to CV square by 2. Therefore, and we also know that capacitance is given by a formula epsilon naught A by D. Using these two formulae, that is U is equal to C square by 2 and C is equal to epsilon naught A by D, and also using V is equal to ED, we get, therefore CV square half C is epsilon naught A by D and V is value of V is formula for V is ED square. This is, we are combining three formulas. One is U is equal to CV square. We are substituting the value of C and we are substituting the formula for V. So, and U as it is on the left side U, and we are dividing this A and the D square. This 1D gets cancelled with 1D and 1D remains in the numerator, that is brought here. Therefore, left hand side becomes U over AD. So, right hand side will be this epsilon naught same, okay, and this E square, E whole square becomes E square, epsilon naught E square divided by 2. But we know A into D, area into the distance, is the volume of the capacitor. Therefore, energy density of electric field is U bar is equal to potential energy per volume, that is equal to epsilon naught E square by 2. So, we are repeating this equation. Energy density U bar is equal to U by AD by definition, that is equal to epsilon naught E square by 2. Let this be equation 2.29. Hence, energy stored is half CV square or Q square by 2 CV or QV by 2, any of these formula, and energy density is U by AD, Therefore, that becomes epsilon naught E square by 2. This also will be required for solving numerical problems. Effect of dielectric on capacitance. In dielectric type of capacitors, the space between the conductors is filled with a dielectric material like mica, plastic, etc. to increase the value of capacitance by a factor K, which is called dielectric constant. We have studied in section 2b about the effect of adding a dielectric between two parallel plate conductors. Here we are seeing in detail what will happen to the value of capacitance if we add a material like mica or plastic or porcelain or paper or rubber between the two plates. These materials are called dielectric materials. So when we add dielectric materials between the two plates, the value of capacitance increases by a factor K, and K is called dielectric constant. Hence, the permittivity constant of free space is modified as K into epsilon naught. The dielectric induces charges on surface which weakens the electric field between the plate. Please note two important points in this section. Dielectric material increases the value of capacitance. Please underline, increases the value of capacitance, and the permittivity constant epsilon naught is modified as K times epsilon naught, and the dielectric induces the charges on the surface which weakens the electric field between the plates. We have different types of dielectric material: vacuum, air, porcelain, pyrex, paper, rubber, and mica are the some of the dielectric materials. Now we have to see the dielectric strength, which is expressed as kilovolts per millimeter. The dielectric strength of vacuum is infinity. That means dielectric strength is nothing but the breakdown voltage of the material. When we increase the supply voltage, the material withstands to certain extent the high voltage, and after reaching its dielectric strength, it breaks down. So dielectric strength of air is 0.8 to 1. Porcelain is 4 to 8. And pyrex material, the dielectric strength is 14. For paper, the dielectric strength is 14 to 16. For rubber, it is 21. And for mica, the dielectric strength is 100 to 200 kilovolts. So mica is a very good dielectric material which can withstand high voltage up to 100 kilovolts to 200 kilovolts per mm. Having studied the dielectric strength, let us see what happens to the electrical characteristics of the material. For vacuum and without dielectric and with the dielectric, the surface charge density sigma remains same in vacuum, and if we add dielectric, it gets reduced by sigma p. That means sigma minus sigma p will be the new surface charge density when we add a dielectric. Electric field in vacuum will be E naught is equal to sigma by epsilon naught, and hence electric field in dielectric will be E is equal to sigma minus sigma p divided by epsilon. That means the charge density gets reduced by a factor sigma p. The potential of the system will be V naught in vacuum will be V naught is equal to E naught into D. But E naught gets reduced by sigma minus sigma p. Hence, value of potential will be in dielectric medium will be sigma minus sigma p over epsilon naught into D. Actual capacitance is equal to C naught is equal to sigma naught by V naught, that is equal to epsilon naught A by D in vacuum. In dielectric medium, the value of capacitance will be C is equal to Q by V, that is equal to A into K times epsilon naught by D. A remains as it is and D is also same, only epsilon naught changes is substituted by K into epsilon naught. So, capacitance increases by a factor K. Permittivity. Permittivity in vacuum is epsilon naught, and when we add a dielectric media, the permittivity becomes epsilon, and that is given by epsilon is equal to epsilon naught permittivity of vacuum into the dielectric constant. Surface charge density, this is already given. Dielectric constant K is equal to 1 for vacuum and K is greater than 1. Therefore, K is equal to epsilon naught by epsilon by epsilon naught. I repeat, K is equal to epsilon by epsilon naught, that is equal to C by C naught. So, dielectric increases the capacitance, but electric field gets reduced inside the surface. The potential also gets reduced. Capacitors in dielectric. We have different types of capacitors: parallel plate capacitors, spherical body capacitors, concentric spherical plates, isolated spheres, and cylindrical capacitors. Different shapes of these combinations are given on the right hand side. For a parallel plate capacitor, the capacitance is given by epsilon naught A by D. For a spherical body with a radius capital R, the capacitance is given by C is equal to 4 pi epsilon naught R. Concentric spherical plates. See, these are the concentric spherical plates, and it has got dimension inner diameter B and outer diameter, inner diameter A and outer diameter B. So, there are two diameters of concentric spherical plates, and its capacitance value is given by 4 pi epsilon naught A into B divided by A minus B. Isolated sphere is 4 pi epsilon naught into R. As isolated means only inner portion is there and B tends to infinity. It is infinity and only inner cylinder will be there. So, its capacitance value is given by 4 pi epsilon naught R. For cylindrical, that is two long coaxial, that is the center is same, coaxial means center is same and there is an inner conductor and outer conductor, coaxial cylinders of length A. This is the length A and radii A and B. The capacitance is given by C is equal to 2 pi epsilon naught L divided by natural log B by A. These are the values of capacitance related to the physical dimension of the capacitor. Parallel plate capacitor physical dimensions A into D, cylindrical 4 pi R square, and similarly for concentric spheres the respective dimensions are given and the capacitance value is also given in vacuum in this column number 2. When we add dielectric between these two parallel plates, or between these two radii or between the inner and outer conductor, the value of capacitance gets changed. So, in case of a parallel plate capacitor, when we add a dielectric, C becomes C is equal to epsilon naught epsilon r into A by D. Epsilon r is the relative permittivity of the dielectric material. So, we add here a dielectric material with relative permittivity as ER, epsilon r. So, capacitance value is changed from epsilon naught A by D to C is equal to epsilon naught epsilon r A by D. Similarly, for a spherical body, the value of epsilon naught becomes epsilon naught epsilon r. So, capacitance is given by 4 pi r into epsilon naught epsilon r. The revised values of for a concentric sphere is also given. C is equal to 4 pi epsilon naught epsilon r A into B divided by A minus B. Isolated sphere. In isolated sphere, it is 4 pi epsilon naught epsilon r into capital R. For cylindrical capacitor, the value is C is equal to 2 pi epsilon naught epsilon r into L, capital L, length of the cylinder, divided by natural log B by A. Now, having studied about the capacitors, now we will take up a device called Van de Graaff generator. Van de Graaff generator is an electrostatic device capable of producing high potential difference of few million volts. Please note, Van de Graaff generates a very high potential difference to the extent of million volts and fields close to the breakdown of field of air, which is about 3 into 106 volts per meter. So, Van de Graaff generator is an electrostatic device for breaking certain atoms. The figure for Van de Graaff generator is shown on the right hand side. Here at the bottom we have metal brush delivering charge from the source. The charges are inlet into it. This brush is driven by a pulley. This is a motor pulley and this is a ground based. This is at the ground and there is a pulley on the upper side, on the higher side also. So, this is a electric support, insulating support column. There are two columns placed on the ground platform and another bigger shell is mounted on the top. This is the diagram for Van de Graaff generator. The schematic diagram of Van de Graaff generator is given in figure. A large spherical conducting shell. This is a large spherical conducting shell of few meters radius is supported at height several meters above. This is several meters above the ground on an insulating column. A long narrow endless belt. This is the endless belt. Endless belt of insulating material. This is a rubber belt or a silk belt is wound around the two pulleys. Two pulleys are, this is one pulley and this is another pulley. There are two pulleys connected through a belt, rubber belt. One at ground level and another at the center of the shell. This is the center of the shell and the other one is mounted at the center of the shell. This belt is continuously moving by a motor driving the lower pulley. Hence, this pulley is connected to a motor. As we are delivering charges here, the belt continuously carries positive charges. See, positive charges are moving from here to the upper pulley. Positive sprayed onto it by a brush at the ground level to the top. So, This pulley through belt is sending positive charges. There it transfers its positive charge to another conducting brush connected to a large shell. So it transfers, this is a brush connected here, and it transfers charge from this place to this bigger shell. Thus the positive charge is transferred to the shell where it spreads out. These positive charges from here, they go up, and through this brush they go here, and it is spread all over the larger spherical shell, where it spreads uniformly on the outer surface. In this way, the voltage difference as much as 6 to 8 million volts with respect to the ground can be built. So, the potential difference between ground to the upper will be around 6 to 8 million volts. Van de Graaff generator is used to accelerate charged particles like protons, neutrons, and other alpha particles. The beam of positively charged particle is used to treat the cancer. So, these positively charged particles are used for treating cancer patients. The positively charged accelerated particles trigger the nuclear reactions. This accelerated beam is also used to break atoms in various physics experiments. It is also used for producing electric sparks. So, I will repeat the contents of this slide under section 2.15. Van de Graaff generator is an electrostatic device capable of producing high potential difference. It is made up of a large spherical shell a few meters in radius, supported by insulating columns and a narrow belt of insulating material at the bottom. The two pulleys at the ground and at the top are connected through a belt. The belt is continuously moving through a motor driven pulley at the bottom. The charges are fed at the bottom, positive charges are fed at the bottom through the metal brush and transferred through the belt to a upper pulley, and from there, using a metal brush, we transfer these charges to the larger shell. Hence, in this way, the voltage difference of 6 to 8 million is built up. Van de Graaff is used extensively to accelerate charged particles like protons, neutrons, and alpha particles. This beam is used for treating cancer also and helpful in nuclear reactions. The accelerated beam is also used to break atoms in physics experiments. It is also used for producing electric sparks. With this, we come to the end of this section. In the next section, we will study we will summarize the whole chapter and take up numerical examples. Thank you.